Our next speaker is Professor Karen Willcox, University of Texas at Austin, and Kiwi, member of the New Zealand Order of Merit, and a big champion of multicore world.
All right, thank you, Nicholas. It's always a pleasure to be here. So you asked us to introduce ourselves, so I'm going to try with a pepeha. Tēnā koutou, I whānau mai o I tupu ake o I tamaki makoro. He haerenga tāku ki wiwi, ki wawa, o nā tau I tini. Ko muriwai, toku tūranga waiwai, ko Karen Willcox, toku ingwa. So I said I was born and raised in Tamaki Makaurau, Auckland. My travels have taken me across the world over many years. Muriwai is my tūranga waiwai, my special place where my roots are, and my name is Karen Willcox. All right, kia ora. All right, woo, that's on camera. Okay, sorry to disappoint you, Ilke. Normally I talk about digital twins at this meeting, but today I decided to talk about our work in reduced order modeling. I will touch on digital twins just a little bit towards the end. Before I started, I did want to just say a little bit about the Odin Institute, for those who are not familiar with it. So the Odin Institute at the University of Texas at Austin, we're the sister institute to TAC, the Texas Advanced Computing Center. We're really focused on computational science and engineering. So as you see here, mathematical and statistical foundations for new methods, scalable algorithms, HPC. In many ways, we're like the science, engineering, medicine users of all the incredible technologies that many people here are advancing. We have been around for many years, almost as many years as I have been around. So 1973, Tinsley Odin founded the Institute, really pretty remarkable to think about what he saw coming. Today, we have grown to be much bigger and much broader. We have 27 faculty that are hired by the Institute, and then another 125 faculty from across campus that are engaged. So altogether, more than 150 faculty. And those faculty come from 28 different departments. So we're cutting across engineering, the medical school, the business school, all of the natural sciences, mathematics, computer science, the geosciences, pharmacy, all kinds of faculty coming together around computing. It really is a wonderful place, and I will certainly invite you all, if you are passing through Austin, please come visit us. Yesterday we saw, Simon showed the picture of the king-to-be visiting. I was looking for my picture of you visiting, Nicholas, but I didn't have it on my computer. But that was the best I could do. But seriously, it is a wonderful place. Come visit me, and then you can pop up to the Pickle campus and visit Dan and see TAC. All right. So to get started, I just wanted to start with a sort of a few high-level thoughts of where I see we are in terms of computing for complex systems. And when I say complex systems, I'm really going to be talking about applications in engineering, science, and medicine. My own home discipline is aerospace engineering, but through the work with the Odin Institute, I've actually been starting to get dragged into a number of things, including some recent work in computational medicine. So, we can think about forward simulations. Forward simulations have been advancing scientific discovery and engineering innovation for many, many decades. And in fact, the field of aerospace engineering is some of the places where the very first forward simulations, the roots of the finite element method, stretching back to structural analysis, those roots go back to the 1950s. Again, it's pretty remarkable to think about those early calculations and the machines that they were doing them on. So forward simulation, the backbone certainly of engineering analysis for many decades. But I think it's really important to recognize that the use of computing for complex systems is much more than just forward simulation. And what is that much more? So decades and decades of forward simulations. We think around the 1970s, really into the 1980s and 1990s, we started to see optimization and inverse problems making their way to impact, particularly again in engineering. So the 80s and 90s were the time where large-scale optimization methods were starting to be used to design commercial aircraft, the aircraft we fly on today. Those wings are shaped by sophisticated optimization methods wrapped around sophisticated computational fluid dynamics solvers. And then inverse problems and applications like the oil and gas industry being used to characterize subsurface and, again, drive innovation and advanced technology. Then you fast forward just a little further in time, and uncertainty quantification really became a big focus. And a lot of this was driven actually by the US signing on to the nuclear test ban, meaning that a lot of that nuclear testing and certification needed to move from the physical world into the virtual world, and that drove a huge effort within the Department of Energy to be able to quantify uncertainties and really be very confident in the predictions that were made by computational tools. And so we saw that happening in the early 2000s, and really for the last 2 decades, uncertainty quantification has become a major topic for those who are using computational methods to drive design and decision-making, to start thinking about those uncertainties and what that means for assessing risks, design under uncertainty. And then that brings us to the last decade or so, where we're starting to see machine learning and AI now everywhere thrown into the mix. So, I think this is one way to think about the landscape of computing for these complex systems. But for sure, this part of the chart, uncertainty quantification, machine learning, and AI, I believe are very much still in their infancy. If you look, for example, out to the aerospace engineering industry, forward simulations are now quite widely accepted. And by the way, I don't say that lightly. When I was doing my PhD, there was almost no trust of computational fluid dynamics in the aerospace engineering. They've finally sort of gotten their head around that. So forward simulations are well ingrained. Optimization is also fairly well ingrained. Uncertainty quantification is just now starting to become out there in the industry, and machine learning and AI, again, really at the infancy. And then the second part of it down here at the bottom is we haven't yet seen the full impact across the life cycle. And by that, what I mean is that I think the design community have always been more sophisticated users of computation. But as we start to think about the rest of the life cycle of an engineering system into the manufacturing and into the test and evaluation, then ultimately into operation, there are so many opportunities for computation to start revolutionizing those pieces of the life cycle. And that's really what brings us to the digital twin concept, which I'll talk about at the end. Okay, so what does all this mean? Well, this means that physics-based models, and as I go through my talk, you will hear that I still deeply believe in conservation of mass, momentum, and energy, and I tend to be rather skeptical of AI methods that don't necessarily encode the physics. Physics-based models are powerful. They bring predictive capabilities. This is really what has allowed aerospace engineers or folks in the energy complex to take such complex systems, represent them in the computer, and drive decision-making that actually plays out reliably in the real world. It's this predictive nature of physics-based models. But as we now start to think about this picture that takes us beyond just a forward simulation and says, I want to do more than just run a forward simulation. I want to put that forward simulation in a design loop, in an optimal control loop, in an uncertainty quantification loop, or in some kind of an inverse problem. These forward simulations are just too expensive. And I'll come back to this problem at the end. This is some work that we've been doing with the Air Force Research Lab. They're very interested in this concept of a rotating detonation rocket engine, which is a concept for future propulsion, for future rocket engine that is mechanically very simple. It's basically a detonation wave in an annulus that can generate a lot of thrust. But the trick is to get the design, and particularly get the design of the injection, the fuel injection, if you can see the little holes around the edge here, done in such a way that you can actually control this thing and make it stable. These are incredibly complex reacting flows. that require very fine spatial degrees of freedom to represent the structure. They require tiny time steps, so time steps on the order of a nanosecond, but you want to be able to simulate out over seconds of this engine operating. When each simulation takes days or even weeks on a supercomputer, it is just an impossible task to think about doing thousands and thousands and thousands of these simulations, looking over the design space to understand what the different options would be. And of course, this is another example where building these things and trying them out in the real world is of course expensive, dangerous, and somewhat intractable. So this is where we need to reach for our favorite kind of surrogate model. And of course, we hear a lot about machine learning-based surrogates, particularly neural network-based neural operators. I'm going to talk today about, I guess, what could be considered a more classical class of surrogates, and that is reduced order models. So shown here in the picture, what's the idea? The idea is that we're going to start with some high-fidelity physics-based simulation. And I first just want to emphasize this. This is not a problem where we don't know the physics, and the goal is to somehow discover the physics. There are problems like that. In at least the problems that I work on as an aerospace engineer, we actually know what the physics is, or are, conservation of mass, momentum, and energy. There may be constitutive models and things that are a little unclear, but the general physics is given to us. And more often than not, we have a high-fidelity model that we trust enough. The problem is that it's just too expensive for the tasks at hand. So the starting point is our high-fidelity model. It's typically very high dimension because we're talking about discretization of partial differential equations, and the solution time is minutes, hours, days, maybe even weeks. And what we're going to try to do is go down to a reduced order model that has much smaller dimension and will solve in much less time, solve in seconds or even fraction of a second. How do these methods work? There's first a training step where there needs to be some kind of representative solutions of these large-scale systems generated. These training data are usually called snapshots. So a snapshot is a solution at a particular point in time or for a particular choice of parameters. Then there's a mathematical step where from the training data, we identify a low-dimensional manifold. And then there's a third step where we bring the physics back in. And one thing that is quite fascinating to me is that if I hadn't put this third step up, you would have said, well, Karen, you're just talking about machine learning. And in fact, machine learning and reduced order modeling, and I'll get to this on the next slide, I think are actually very near intellectual neighbors. That yes, this idea of training and identifying structure is is in common with machine learning, but this third step is where the physics comes back in, to take the governing physical equations and mathematically actually project them onto this low-dimensional manifold. In other words, look for the evolution of the equations in this low-dimensional manifold. That's what gets you the reduced order modeling. So just to pull a little more on this kind of difference between model reduction and machine learning, actually I didn't update these slides. The definition of machine learning is always changing on Wikipedia. I don't know if it's dueling groups that go in there and edit it, but anyway, at some point in time, machine learning, a field of study in AI concerned with the development and study of statistical algorithms that can learn from data and generalize to unseen data and thus perform tasks without explicit instructions. Reduced order modeling, a technique for reducing the computational complexity of mathematical models in numerical simulations, closely related to the concept of meta-modeling. So these sound quite different, but to me, really, the difference is that I think of machine learning as an outside-in view. It says, give me a bunch of data, give me this training data, and I will look at that data in an observational way, and from that data, I will try to infer and come up with a representation, probably using my favorite neural network architecture. In contrast, reduced order modeling is an inside-out view, which says start with the physics, start with the model that you can write down but maybe can't solve, and build from that model from the inside out to get to this reduced order modeling. So I co-authored a paper a few years ago where we kind of noted this contrast. And in many ways, what is different about the field is the places they've come from. Machine learning's come from computer science, where, I don't know if I'm going to offend the computer science, everything is a pile of data. You just need enough training and algorithms to make sense of it. Reduced order modeling really came from computational science, where everything is all about the physics, and then it's about querying that physics in such a way to find these reduced order models. But when you start to dig down into some of the methods, there are actually incredible similarities. And of course, the power, and by the way, we have seen this outside in and inside out view in fields like biology that started off as an observational science and then transitioned to inside out views as we started to be able to build these incredibly detailed representations. The power comes when you can put the two together, to put the two views together. And so before I talk about putting them together, just thinking about some of the pros and cons. So in machine learning with this outside-in view, the models may or may not generalize. I think the community is starting to make a little bit of progress in addressing this, but the reality is that for the kinds of complex physics problems we work on, we can build a machine learning model that matches the training data. We have no idea when we start to run it outside the training data what kinds of answers we're getting. The large training data requirements are absolutely excessive, and I'll come back to this at the end. This is a huge, huge problem, and I think it's a huge cultural problem in the community because it's a problem that people just don't seem to acknowledge. The training data requirements for real problems are absolutely prohibitive. And that's just not something that's going to make its way into the real world unless we address it. On the plus side, these methods are non-intrusive, they're portable, they're flexible, they're accessible, and they're available. And so for all these reasons, they have massive uptake in the outside of the expert community. It's really, really quite easy to use some of these machine learning methods. In contrast, reduced order modeling has a deep body of theory and methods. Depending on the problem you're solving, there may be very deep theory that gives you, for example, error estimators, in some case error bounds, so that you can very rigorously say how good is the reduced order model when you run it for conditions that you did not train it on. There is theory that relates to stability, theory methods that let you preserve certain structure, knowing that structure reflects different symmetries, which in turn enforce different physical properties. So a deep body of theories and methods, but it's a highly expert community. The methods are inaccessible and intrusive, meaning that you have to take your high-fidelity simulation code and then probably spend months, if not years, trying to implement the reduced order modeling methods inside it. And so for these reasons, really limited uptake outside the expert community. So what we've been doing over the last decade or so in my group is to try to get the best of both worlds, to say, why can't we be non-intrusive, portable, and flexible, just like machine learning, but at the same time, do we really have to throw away the deep body of theory that comes from the inside-out view of embedding the physics? And we try to get the best of both worlds through a method that we call operator inference, which is going to take the inside-out view in saying that I know the physics, I know what form the physics comes to me in because I can write down the governing equations, and then I know what form those equations are going to take when I discretize them. But I'm not going to build the reduced order model by doing all these intrusive mathematical operations. Instead, I'm going to try to infer the reduced order model, machine learning style, from data that are generated, but through the lens of this structured system. And without sort of overwhelming you with too much math and linear algebra, I want to just give you a little bit of a sense of how this works, but I'll skip over. And this line here is important. The idea is to get these reduced order models that will solve in a fraction of a second, which gets those physics predictive models off the supercomputers and into the operational world. So this work all started, this paper is 2016. This is Benjamin Peerstoffer, who was a postdoc with me at MIT at the time. Benjamin's now a professor at the Caron Institute at NYU. So what is the operator inference problem? Again, we are concerned with problems where we have known governing equations, and we're going to need this training data, set of data in the form of either these state snapshots that might come from simulation, or a really interesting question is, what if you also have experimental data, and how could you put the two together? And again, we're going to try to infer a reduced order model that recovers the given data and provides a predictive capability to rapidly simulate unseen conditions. So the answer to this problem is simple. It's linear algebra. Everything, I believe, almost everything in this world is linear algebra at some level or another. Basically, and again, I'm not going to go through the whole details of the formulation. I'll give you a little hint. But basically, we end up solving this linear algebra problem where we're going to have data D. These are the snapshots. We're going to be inferring operators O that define this reduced order model, and we're going to have a right-hand side term. And in getting to this linear algebra formulation, we've got the physics that are, again, giving us the structure of the model we seek. We use the theory of projection-based reduced order model, which tells us what is the structure of this model you're looking for, that is an evolution in the low-dimensional manifold. There's inverse theory that comes in, and by the way, this is another thing that, boy, do I wish some of the machine learning people would pay more attention to. Just because you have a pile of data does not necessarily mean that you can characterize different parameters. So inverse theory to analyze the structure of the resulting problem and to have appropriate numerical treatment for ill conditioning, and then everything is implemented numerical linear algebra so that we get scalable algorithms. Well, it's maybe a little too, I don't know, late in the week or early in the morning for too much linear algebra. But this is the theory of projection-based reduced order modeling. And really what's important on this slide is that if you start with a large-scale system that has a particular structure, and I'm showing you here just a linear system because it's easy to see. So where do these kinds of operators, these linear operators, show up? If you have, for example, diffusion terms in your governing partial differential equation, when you discretize these diffusion terms, you might end up with a linear operator like this A here. What's important about projection-based theory, the inside-out view, is that when you view the task of dimension reduction as this projection onto, in this particular example, a low-dimensional subspace, the reduced order model inherits the form of the model that you started with. And this is true not just for linear systems, it's true for any system that's got a polynomial nonlinearity in it. It's also true for other kinds of systems. And some of the other things that we have been able to show is that even nonlinear terms that show up in things like reaction equations, where you have different kinds of nonlinearities, you can play games with changing the physical variables you're working in. And for many, many, many physics models, you can actually write them in a quadratic form. And that's what we're looking at here, a linear term and then a quadratic term. So said another way, you can take the governing equations of physics, you can play clever tricks on variable transformations and clever choice of the variables you work in. You can then write notionally your high fidelity model in this polynomial form. And then what you know is that the reduced order model that you are seeking will also inherit this polynomial form. So putting all this together, and again, I'm going to go quickly through this, gets ultimately to solving this large-scale linear problem where we are now inferring those operators that are defined in this form given to us by the physics. Over the last 10 years, a number of my students and postdocs have worked on different aspects of this. So showing how we deal with nonlinear systems that don't have polynomial form. We've done a lot of work in looking at numerical regularization and how to address ill conditioning of the learning problem. Looking at embedding parametric dependence, which is really important if these reduced order models are going to be used for design or control or uncertainty quantification. Different ways to embed uncertainty. We've done some work in representing the dynamics on quadratic manifolds rather than linear subspaces. This is particularly important for transport-dominated phenomena, which can be hard to characterize in linear subspaces. Some work in distributed formulation that really has large-scale block structured, what happens when you have multiple interacting physics, and there's more structure that you want to embed in the reduced order model, and then nested operator inference, which is inheriting more properties of the system. So all that is a way to say it's a rather flexible framework that really gives you a lot of hooks to be able to embed more and more and more structure into these reduced order models. So let me come back to this rotating detonation rocket engine and just give you a sense of what's possible. So as I mentioned, it's the reactive Navier-Stokes equation. So the high-fidelity code is a large eddy simulation with a particular chemistry model. There are the governing partial differential equations, conservation of mass, momentum, and energy, conservation of chemical species, whole lot going on there. This LES code, this is an Air Force code. We don't touch it. It's written in Fortran, like most good aerospace codes. We don't touch it. We don't have it. And this is, again, one of the sort of key innovations of the work is that we don't have to go into the source code to implement these intrusive reduced order models. We're going to be dealing with everything at the level of data. So the first thing is to generate the training data, and I am going to come back to this point because this is really a bottleneck. But the training data are going to come now from these large eddy simulations over different parameter values, different design geometries, different values for the injections. One of the terrible travesties of the real world is that the Air Force are burning all these cycles, weeks and weeks of simulation time, and then they can't save all the data. Nanosecond time steps on hundreds of millions of degrees of freedom. They do these runs and they just cannot save all the data. So they throw most of it away. They downsample in space and they really downsample in time. And they save like of the order of 500 out of 500,000 snapshots. Again, we could talk about that, but there is such a need for methods that could do some kind of in situ dimension reduction and compression, even just for helping to be able to save more simulations. Anyway, so we get massively downsampled data sets from them. There are 18 state variables because you've got to have mass, momentum, energy, and then all the chemical species. We play a lot of tricks in the variable transformations, and then ultimately we end up with our snapshot matrix of being dimension 76 million by 375. So 375, that's the number of snapshots that we end up having. At the core, the workhorse of the dimension reduction is the singular value decomposition, quite possibly one of my favorite things in the world. Again, we can argue about this in the break and over lunch. I know neural networks are incredibly powerful and expressive, but I deeply believe that a low-rank representation by a singular value decomposition will get you 90% of the way in some vast number of engineering problems. And I think we as a community need to be asking ourselves whether we are reaching for neural networks because they are truly needed for a particular nonlinear problem, or whether a more interpretable SVD would do the job. So I'm a big fan of the SVD. We have to be very careful about the way we process the snapshots, do the singular value decomposition just because of the scale of the problem. And then the last part here, that's solving that linear optimization problem to infer the reduced models. We have been running on Dan's machines, on Frontier at TAC. Maybe not surprising, the method scales really well because at the end of the day, everything is pretty much linear algebra. You can see that just reading the snapshots in and out is actually a huge part of the computational load and the part that really doesn't scale very well. So this is the kind of result we can achieve. And one thing I will always say, there is no magic. There is no magic, and if the results you're looking at in a paper are magical, then you probably should be very skeptical of them. We're going to go from 76 million degrees of freedom. So this is the downsampled grid. It started off at 136 million. Our reduced order model has 24 degrees of freedom. So we are evolving this reduced model in a low-dimensional manifold that has 24 degrees of freedom. There is no magic. I am never going to replicate all the details of this complex flow field with 24 degrees of freedom. But what you can see here and what we're looking at here is the pressure. We're looking at the pressure going around the annulus of this rotating detonation rocket engine. And we're looking at a time just at the end of training. And then these ones here are predictions now out in time beyond where we had those training data snapshots. And then the 3 going this way, this is close to the injectors, sort of at the front of the engine. This is inside the detonation region, and this is outside the detonation region. And what do you see? You see the reduced order model actually gets the low order behavior pretty well. It's getting the frequency of the wave, it's getting the magnitudes of the wave pretty well. It is not getting the high frequency oscillations that you see here. You can then start to look, for example, at some of the pressure contours. So let's see, at the top here, we're looking at the full LES solution, the top and the middle. Down here at the bottom is the reduced order model. And again, what you see is that, of course, it's not getting all the fine-grained detail that you get when you have this 130 million degree of freedom grid, but what it's getting is sort of the global scale behavior. And one of the happiest days of my life is when one of the combustion guys from the Air Force said to me, actually, you know what, Karen, I would actually prefer to look at the solutions coming out of your reduced order model because that's going to give me a lot more physical insight as to what's going on. Sometimes these high-fidelity simulations are a bit overwhelming. So all that is to say that these reduced order models, which, by the way, run in less than a second on a laptop, can be incredibly useful even if they are not capturing every last detail of the behavior, and they're also interpretable. Okay, in the last 4 minutes, looking to the future, so just coming back to that picture, I think it's a pretty exciting time because while there are still massive challenges here, it's incredible the number of problems across engineering and medicine particularly that we actually have pretty good handle on the forward simulations. And we are just in the beginning of thinking about how those forward simulations can be wrapped around with these loops to actually drive impact and decision-making in the real world. So as we think about this entire landscape and think about how it all comes together, this is, in one way, what gets us to the idea of a digital twin. A digital twin really builds on everything that I showed in that last slide. It takes forward simulations that are predictive, but includes the optimization, the optimal control, the inverse problem, the uncertainty quantification, the AI, and the machine learning. So digital twins, another big focus, both at the Odin Institute and my own research. Again, I really want to emphasize something I said earlier. I think we, certainly in engineering, have seen a lot of impact of computing in the design part of the life cycle. We are just starting to see interest, particularly through digital twins, in how computing can impact manufacturing and operation. So digital twins for manufacturing, this has been a topic of interest for the past few years. One of the things that's really exciting right now is we've been in a lot of discussions with the Air Force Test Center. We've had a couple of test pilots come to visit us in Texas. There's a real interest in digital twins for flight tests and evaluation. I was actually pretty shocked to learn that in a development of a military aircraft, the test and evaluation accounts for about 1/4 of the budget and takes years and years and years. And so thinking about how digital twin technology could cause you to be more efficient in the use of flight test resources is a really, really exciting and frontier problem. So I am very excited to see digital twins bringing computing further out into the life cycle of complex problems. But of course, as we think about this grander vision, there are so many challenges. When it comes to reduced order models, there have been so many advances over the last decades, even if they are all overshadowed by the popularity of machine learning. But we still need to scale our methods to really be able to handle the complexity and the wide range of operating conditions for many digital twin applications. There's also huge interest in medical digital twins. This is an area where I think the capabilities for both forward simulation and reduced order modeling lags. And I want to finish on this last point because I think it is an incredibly important one. The cost of training data is a huge barrier. So the snapshots that we are generating with the Air Force for this rotating detonation rocket engine is a minimal amount. You saw at the end we had 375 instances in time, and that took weeks on their supercomputer to get. There is no way we could train a neural network, I don't believe. Maybe I would like someone to prove me wrong. I don't think it's even close to enough data to actually be able to train a neural operator, which is one of the reasons we're working with these singular value decomposition. But even so, the cost of the training data is prohibitive, and this is something that keeps getting swept under the rug or ignored in academic problems. So I think this is one area where there's just a huge research need, whether it's more classical reduced order modeling methods or your favorite neural operator. How do we overcome the barrier of the training data? So with that, I will close. I will point out the website is kiwi.odin.utexas.edu, and again, I welcome questions. Thank you.
Thank you very much, Karen. Fantastic.